So just to provide a quick review before we get into the new material with liquid penetrant inspection, starting off with first, remember there are two types, type 1, type 2 for your actual penetrant. Type 1 is fluorescent and is viewed with a black light. Type 2 is your visible dye and viewed under white light or normal what we consider light. Uh, there are 5 sensitivity levels that we can buy penetrants in. Starting with 1/2 and then 1, 2, 3, and 4. And the visible penetrants, the red that you saw on the previous slide, those are a level 1 penetrant. That's the highest and pretty much the only level they come in. You really don't see level 1/2 anymore. There's really no reason to go that low. And then to get a level 2, 3, or 4, you have to use some kind of fluorescent penetrant. The ones we'll be using in lab are going to be level 2 penetrants, and that's the kind of the standard for most uses in aerospace. You may have some very specific uses where you got to go to level 3 or level 4, but for daily use or in the what I would call shop floor use, level 2 is probably going to be your most common. And again, level 1, the visible penetrants can be used in general aviation oftentimes, but most of the time in transport aviation, corporate stuff, business jets, passenger aircraft, passenger jets, cargo, that's going to be, you're going to have to use those fluorescent penetrants at a level 2. The bigger manufacturers, the Boeings and the Airbuses, and then the Pratt & Whitneys and GEs, they don't, their minimum is that level 2. And then we talked about penetrant characteristics, what makes the penetrants do what they need to do, which is ultimately capillary action to pull that penetrant into those cracks, discontinuities, corrosion areas, and wetting to be able to spread across surface. And then we talked about how to remove the excess penetrant. So we're going to apply the penetrant, it's going to wick into those areas, and then we have to remove the excess. And removing the excess, there's 4 different wash methods. A is using water. I'm going to skip the C as solvent removal, typically in aerosol form. And then B and D are your post-emulsifiable methods that require an extra step during the rinse process of applying an emulsifier. B being a lipid-based emulsifier or lipophilic. It's primarily going to bond more to the oily side of the molecule. And then method D being hydrophilic. It's going to bond more tightly to water. So we looked at those. And then we were starting to look at developers. So the developer is used after we have applied a penetrant, allowed it to dwell and soak into those areas. Now we need to, and then we clean the excess off. Now we need to be able to see where that penetrant has stayed behind, where it's been trapped in those different areas. And so we use developer in order to do that. And it works with blotting action, or wicking, which is, you can think of it like putting a paper towel on water, right? You set the paper towel on, it's going to pull that water back up, even if it's down in little crevices or that kind of thing, on not a surface that isn't necessarily 100% smooth. So the penetrant works the same way, and by pulling it back up, it pulls whatever dye was trapped in those areas back up to the surface where now we can see it, where it'll be either visible, if it's a type 2 penetrant, red, or we can shine a black light on it and it'll glow as a type 1 fluorescent penetrant. It also enhances that fluorescent action. Part of it is, the cracks we're finding are very, very small. They're not visible to the naked eye. And so part of that blotting action is that penetrant comes back up as it spreads out a little bit. So it magnifies the crack. It makes it look slightly bigger than what it is, so it's actually big enough that we can see it. If you're using aerosol type penetrants or other ones that coat the surface, they're also going to leave a white or light colored coating on the surface, which is going to provide some kind of a contrast background. So you'll either have a red visible penetrant on a white background, or you'll have a bright yellow green fluorescing against a white background. However, not all developers do leave that background. Some of them are transparent or clear, and then it's purely using that blotting action to pull the dye back up to that surface. And with these, when we do develop, which sometimes you'll hear it referred to as a dwell time as well, penetrant, we let it dwell. Developer, you'll hear it referred to as letting it dwell, or I like to use develop so that it's kind of two different things. But the developing time on there is roughly that 10 to 20 minutes, although you can start looking at it as early as you want, right? Once it's on there and it starts pulling that up, you can look at it. As long as you don't wipe it off, wipe it away, it's going to continue to do that wicking process and continue to develop. And you can look at it 10 minutes, 20 minutes, and sometimes even upwards of like an hour or more. Hey, everyone's looking over at the jet taking off. I think it was a Falcon, right? You might use liquid penetrant on the jet that just took off. Maybe it had some inspections done. So developers are divided into 6 different forms. Form A, B, C, D, E, and F. And these refer to the kind of what the form, what medium that developer is. And so Form A is known as a dry powder developer. You can see B and C are water-based, water-soluble, and water-suspendable. Form D and E are non-aqueous or solvent-based. And then Form F is actually kind of a catch-all collection of special applications. It's funny. Trying to get my Windows bar to go away there. I don't know why it's staying up. But anyways. So a little more detail, Form A, dry powder, it's used commonly with, type 1 methods. So it's used with fluorescent. It's not great to use with the red dye because this is one, dry powder does not leave any kind of a surface coating. So it's not as good at creating that contrast for a visible dye, but it works really well with a fluorescent dye. And so what we have is, it's considered the least user-friendly just because of the dust factor. When you use this in lab, this is one we use in lab, you'll see it is very easy to get dust from it kicked up in the air. And it's essentially a very fine dust, a very fine dry powder. And each one of those little particles, what you see is not actually the developer, it's a carrier. It's a carrier dust. Those little particles themselves are coated with a very thin layer of a chemical developer that is clear. And when that dust essentially rubs across the surface of your part, it leaves that developer behind on the surface. And so then it sticks in those areas where penetrant is present, the developer chemical. And it causes that penetrant to be drawn back out of those cracks and crevices. But it doesn't coat, again, it doesn't coat the entire part. It sticks to those areas where there's some liquid present that kind of that causes that coating to kind of come off and transfer to that slightly wet surface where there's penetrant still present. The nice part though is it's easy to handle and store. As long as you have a lid on it, it's not gonna, it's not a liquid that can leak out if you don't have a sealed lid or something like that. It's pretty lightweight. If you pick up the tub we have it in, it really doesn't weigh much because the dust is so light. And it's very inexpensive. It's one of the most inexpensive means. So if you're doing high volume, if you're doing a lot of parts, commonly you'll use this dry powder developer. And so it's most often used on like a fixed bench at a shop where you're going to be processing a lot of parts one after another. The next two are water-based. So Form B is our water soluble. And so this is used with all penetrants except it can't be used with method A. Remember what method A was? What kind of penetrant was method A? It was what? Water washable. So the problem with this kind of developer is if you have a water washable penetrant and you use a water-based developer, you're going to wash the penetrant away. Okay, so these are used typically with post-emulsifiable ones, where post-emulsifiable penetrants, where once the emulsifier has been washed away during the wash process, then the water will no longer be able to dissolve or carry away that liquid penetrant, that dye, as long as there's no more emulsifier left on the part. So it's not used with method A, but it can be used with method B, and particularly B and D, which are the two post-emulsifiable versions. And in this case, we take a powder. It comes in a powder form. You mix it with water. You typically want to use very good water, probably not the brown water that comes out of our faucets here in Battle Creek, but rather like a distilled water or some kind of an RO type treated or filtered water. And so it will dissolve in there and in the water. And then when we apply it, the water evaporates and leaves behind the penetrant that was dissolved in it. And remember, dissolving means that the penetrant actually, the ions separate, and it actually becomes, it comes in solution with the water. So it doesn't settle out. That's the advantage of it, is that you don't have to constantly be stirring or keeping the your mixed batch of developer agitated in order to keep particles in suspension, which is what we'll see with the Form C next. With any water-based developer, though, it can pose some problems. One is bacteria growth. You know, it's in a wet environment, and so there is the chance of bacteria or other contaminants to grow in there. And then the other part of that is corrosion, right? Moisture can lead to corrosion, and so if it's not handled properly or dried out properly after we're done, it can cause corrosion issues on certain parts. Form C is another water-based, but this one's water suspendable. So now the powder that we get, the developer powder, instead of dissolving in there, is just suspended. And so we have to keep this agitated. It works like the mag particle bath, where if it's not constantly being agitated, all these particles are going to settle to the bottom. And so the water is the carrier to transport those particles onto the part as a developer. We need to make sure it's mixed up, well mixed, before we apply it to our part, so that those particles are in suspension and actually get on the part that we're trying to develop. So this can be used with all penetrants because it doesn't have to, it doesn't, you're not like washing it away. It doesn't act like a solvent as much. But it has a very rapid developing action, because all that happens, those particles transfer, and then the water, instead of having to go, instead of like method or developer Form B, where there has to be kind of a reverse of that chemical dissolving process during the evaporation, in this case, the water itself just evaporates away and those particles are already sitting on the part. And so it has a very rapid action. I mentioned the agitation. But here we don't actually have to dry the part, because we are using a water rinse or something to clean the excess dye off. When we apply this, we don't have to dry the part beforehand. When we're using a dry powder developer, Form A, we have to make sure the part's dry so that the developer doesn't cake everywhere on the surface. And same things, water-based pose bacteria and corrosion problems. Over time, the water will evaporate, so we have to make sure concentration is correct. So these will often be, your levels will be checked similar in a centrifuge tube, similar to what we do with mag particle, where you take a sample and allow it to settle to check the particle concentration in a given volume of fluid. It's not necessarily the 0.2 to 0.4 milliliters of, you know, per 100 milliliters of solution like we have for mag particle. It depends on the developer and what the manufacturer has set for that concentration level. So it can be different for different brands, or even different, you know, different part numbers of developer, different types. Form D and E I have together here because they're effectively pretty much the same thing. In fact, our developer that we're going to use, that's Form DE, is a dual form developer. This is aerosol or solvent based, so it's almost always aerosol solvent based. So used in portable applications. And it can be used with pretty much all types and methods of penetrant. Okay. So technically, you know, you could mix this up with the bench stuff. You could use this on the bench, even though it's more expensive than the dry powder. So again, it lends itself primarily to portable applications where you're doing low volume. You know, one or two things out in like a hanger versus, you know, 50 bolts that are being run through checks one after another in a bench. It's most sensitive, but it's also It's also easy to perform improperly simply because being a solvent-based, not only does that solvent carry the developer, but solvent also does a really good job of dissolving the penetrant, breaking down the oil-based penetrant. And so if you aren't careful with it, it can actually break down, you can overwash the penetrant that you've applied to your part. So we apply it to the part, we apply it in light coats and then let the solvent evaporate, which leaves behind the developer chemical. And this one does leave that white coating on the surface. And D and E, I forgot to mention, form D is when it's being used with a type 1 fluorescent penetrant, and it's referred to as form E if it's used with a type 2 visible penetrant. So that's why it gets the dual form. The developer we have for doing portable is a dual form. It's designed to work with both the type 1 penetrant and the type 2 penetrant that I have available for you to use, which also, like the type 2 penetrant we're using, happens to be probably the most common penetrant that you see in commercial aviation. The final form of developer is known as form F, and form F really isn't a single developer, but rather it is a catch-all for anything that doesn't fall in one of the other 5 categories. And so the common types of this are plastic or lacquer-based developer. What do you think? What's a plastic or lacquer-based? What do you think it does? Think about plastic, you know, it has to be applied as a liquid, and then think of like an epoxy. What happens? The what? Like a film, or it hardens into something. So these are often used when you want a permanent record of something. So it's a developer, but then it actually hardens and leaves a permanent, it's not one you clean off when you're done. And so if you want to have a permanent kind of visibility of an area, you would use these plastic or lacquer based. Almost, again, it's almost like an epoxy that, while it's liquid, it draws that penetrant out and then it hardens and the penetrant is trapped in the plastic or lacquer coating that's now dried on the surface of whatever it is you're testing. And so it has that permanent record of what's being required, and it's typically non-removable. From a chemical aspect, I mean, you could like bead blast and that kind of thing. But as we talked about earlier with pre-cleaning a part, you got to be careful bead blasting a part that you're doing liquid penetrant, because you can actually peen the crack back closed when you bead blast something, and then you won't even get an indication. So when we're working with liquid penetrants in your report or in general, there's some things we have to specify in order for the next person to understand what it was that was done. So we have to do our type of penetrant. Are we doing type 1 or type 2? What's type 1? What's that? Okay, type 2. This is the review slide. Okay, we have 5 sensitivity levels. So if I'm using a type 1 penetrant, sorry, let's start with type 2. If I'm using a type 2 penetrant, what is the sensitivity level we're probably going to have? What? Medium. How about numbers? The scale here. Half, 1, 2, 3, or 4. 1. Visible penetrants type 2 are pretty much all type 1, are all sensitivity level 1. Okay. What about our portable and bench-based liquid penetrants that are type 1 fluorescent? What sensitivity level are we working with here? These are sensitivity level 2. What do you have to be using to get a sensitivity level 3 or 4? Kind of getting into the next step here, into the method. What do you have? What methods of penetrant, what methods of wash do you use for level 3 and 4 penetrants, which are also type 1 fluorescent, but more sensitive? What's that? B and D. What are B and D? What are they referred to? You don't remember the big word? The post-emulsifiables. And The first one is post-emulsifiable, B is post-emulsifiable lipophilic, and D is post-emulsifiable hydrophilic. What's method A? These are wash methods. Remember what is wash method A? What's that? I heard it. Someone said water. Okay. Method A is water. What's method C, wash method? Solvent. Solvent's our last one, typically in a spray can, right? Portable. Okay. And then finally, we have 6 forms of developer. Getting tougher. What's Form A? Form A is dry powder. What's Form B? What are Form B and C? They're water-based. Anyone remember which one's which? So B is water dissolved, and C is water suspendable. How about D and E? What are D and E? They're solvent-based. And which one's used with what? If you have Form D, which type of penetrant is it? Type 1. And Form E is penetrant type 2. And then finally F is special purpose, which can be a whole host of things. So our processing steps, just kind of a review of this. We want to pre-clean our part, apply our penetrant, allow it to dwell. We need to remove the penetrant and rinse. And if we're using a post-emulsifiable, this is also the step where we would be applying our emulsifier before we do the rinse. Then we apply our developer, allow to dwell, and we inspect. So what do these look like? Pre-cleaning, removing any dirt, oil, grease, gasket material, and you must strip paint. You cannot typically perform penetrant on painted parts. Okay? Part of that is if you get cracks or crevices in the paint, they're going to show up as cracks or crevices that may not extend into the metal substrate or into whatever the substrate is. Even, typically liquid penetrant's used on metal. It's not used on composites very often. In fact, you got to be real careful on composites because it can actually wick into the fibers. And you don't want to have a bunch of penetrant permanently absorbed into your fiber structure. Okay. So usually we're going to do some kind of chemical cleaning. Waters, detergents, vapors. The one we're going to use primarily in the lab is isopropyl alcohol. It's a very good solvent. It's a general cleaning solvent. It removes most things. And it also evaporates quickly, not leaving behind any residue. Okay. Do not use any mechanical means. This is what I was talking about. Bead blast, wire wheels, scraping, or sanding, because you can actually peen that surface back closed. You can have a small crack and you can mush the metal back together enough that your penetrant will no longer work its way into those cracks and crevices. Now, it does work sometimes. I just had a part I brought down to the lab the other day. Some of you saw the engine case that we got from Fleet Service. I did hit that with the blast cabinet. It still gets cracks showing up, no problem. Okay. But typically that's not best practice. It's just in my case trying to get something for the lab that works well. I've got 3 more Cirrus struts in the back of my car too. So. After we've pre-cleaned the part, we're going to apply our penetrant. It can be dipped on, sprayed on, brushed on. The key here is that we want to cover the entire surface of the part. Now, if you're using an aerosol-based penetrant, the one thing or any penetrant honestly is, ultimately just remember you have to clean off whatever you've put on, whatever excess is there. So it's not going to hurt it to over-apply the penetrant, right? You can't have too much penetrant in the fact that it's going to affect your ability to get an indication. But what you can have is so much penetrant that it's a royal pain in the butt to get it cleaned back off again. And so, or you're just wasting, product. And that's primarily if you're using aerosol products. When we use the liquid penetrant that we have on the test bench, there's a tub of it there. You just take your part, dunk it in it, dip it, but then we set it on a rack, a drip rack, that allows the excess to run off and back into that bucket or into that tub. And that's during the dwell time. So the dwell time then is how long we're going to leave it on the part. And it can be typically anywhere, minimum is typically about 10 minutes. Pretty much everything you're doing in the lab down here, 10 minutes is going to be sufficient. I just tell students 10 to 20 minutes. Leaving it on a little bit longer isn't going to hurt anything. Okay? The big key is you don't want to leave it so long that the die can actually dry, that the penetrant can dry. Okay? If you let it dry, the risk is that the penetrant will actually clog the cracks. Now, these are oil-based, for the most part, oil-based penetrants. Oil-based things do not dry quickly at all. You know, we're talking, you would have to probably leave the penetrant on for days. The one exception to that is if you're doing something like engine parts. And this is more when you're done, if you don't clean it properly, heat can accelerate that process. And so you don't want to leave penetrant, and ultimately when you get to developing, you don't want to leave developer on, especially on parts that get hot where it can get baked into those cracks. We would do penetrant inspections on the turbine cases of the engines we worked at. You could have a crack up to about 2 inches long, as long as it wasn't exceeding a certain value or didn't grow too much between this inspection and the last inspection. Every once in a while, someone wouldn't clean it properly when they were done, and when we rolled around, we did the inspection again, the crack would shrink. Say we measured it last time at 1.5 inches, and this time we measured it at 1 inch. Cracks in metal do not self-heal. It did not shrink. What happened is it was not properly post-cleaned. It's on a turbine case that gets around 600-700 degrees, and it just baked that stuff in there. And then it is a matter of you're soaking it with alcohol and spraying it with developer and soaking it with alcohol and spraying it with developer and soaking it with alcohol and spraying it. You're doing that over and over and over and over again to try to loosen up that stuff that's in there and using the developer to pull it out. And then loosening up with a solvent and using the developer to pull it out. We had to do it until we at least got, you know, then your question is, did I clean it well enough that I can see any growth, right? So it kind of created a bit of a difficult scenario for whoever was making that judgment call. Did that crack grow too large? When in fact, the first time they tested it, it shrunk. Next is we need to remove the excess penetrant. So method A is water wash. If we have a water washable penetrant, these are still oil-based. They're oil-based, right? Water doesn't do a great job of removing oil. So, you know, I've talked about there's post-emulsifiable penetrants. A method A water wash penetrant has an emulsifier mixed in with it. It is part of the penetrant. And that's what allows water to wash it off. It's not a very good emulsifier because we don't want the water to be able to wash it back out of the cracks. It takes some effort to wash that oil-based dye off, but it is mixed in there so that we can wash it off. So we want to remove the excess, but we don't want to over clean, right? So we got to be careful we don't underwash. If we don't wash enough of it off, a bunch of extra dye or penetrant on the surface can obscure our ability to see relevant indications. If we overwash it, we can actually clean that dye or penetrant back out of those areas where we would hope to get an indication. So water is applied using a coarse flow. That means it's kind of dribbled over, or kind of a stream. You don't want to do like the thumb on the end of the garden hose shooting a stream at it. Okay, patience, a little bit of patience in the wash process is good. Water pressure, 20 to 40 psi. If you're using a hose without any kind of a nozzle, you really don't have much pressure at all, as long as you don't have your faucet cranked. And then our water temperature typically is somewhere between 50 and 100 degrees. I usually recommend somewhere around 80 degrees. That's about what we get on our test bench if you kind of dial it in. But if it's 60 degrees, 70 degrees, 80 degrees, 90, right? Warmer water is going to clean better and more efficiently than colder water. But warmer water also has the potential to overwash and you know, dissolve that dye or pull that dye back out of the cracks more easily. So it's a balancing act. How hot do you make the water? How much pressure do you use? But I don't want to overdo it and not be able to find what it is that I'm trying to find, if it's there. After we wash the part, as long as we're not using a water-based developer, we're going to dry it. And we typically dry it in an oven that's about 150 to 200 degrees. I have 150 to 200. Our oven, you'll probably use it at 104, 120, 140. Really, the temperature isn't such a big deal. The higher the temperature, the faster the water. The main thing is you're just trying to get any water left on the surface, you're just trying to get that off. Because you don't want to have developer stick to that wet surface. That shouldn't. So, I have 150 to 200 here. Our oven actually has an alarm on it if it gets above 165. And really the only time it gets above 165 is if you leave it totally closed for way too long. Okay. But if it's 120, 130, 140, you're just going to want to record that. What temperature did you dry the part at? And how long did you dry it for? Now, part of that too is that temperature is going to change, right? When you first put the part in, it's probably going to be a little bit, you're going to open the door, it's going to let cool air in, it's going to be cooler, and it's going to warm up as it's in there. You can either kind of do a range, you don't have to be super specific on the temperature. Our oven it's got fabric sides, and the thing is a little turkey oven temperature gauge. It's nothing super technical, but it's just to get that surface water off. If you're using method C, solvent removable, again, this is primarily for portable where we're using aerosol cans. You have to keep in mind that the solvent is very aggressive. It's not as aggressive as isopropyl alcohol. That's why isopropyl alcohol is good for pre and post cleaning. It's actually too aggressive for cleaning in between. So there are method C solvents that are specifically for liquid penetrant testing. And you'll use that, but you do not want to apply it directly to the part. If you spray that liquid penetrant or liquid solvent on the part, it is going to dissolve penetrant that's on the surface as well as any penetrant that's down in the flaws. And so what we do here is first dry wipe. Get a clean, dry, the white paper towels that we have, and you're going to wipe off a decent amount of the penetrant using a dry paper towel first, because it actually gets messier when you start mixing the solvent in as well. So we try to get most of the penetrant off with a dry wipe, and then we're going to take a new clean cloth, new clean wipe. We're going to apply the solvent to that, and then we're going to use that to do the final wipe. And when we're doing it, if we have a part, say my water bottle is our part, we don't want to sit here and scrub it. Okay? We want to take our dry wipe, or when we wet it with solvent, and you're going to want to go kind of one direction across the part. Okay, nice and smooth. You don't want to leave it sitting in one spot where it can wick the dye back out of any kind of indication areas. Okay, so nice smooth wipes. Sometimes you can go in a second direction, but again, you don't want to sit here and scrub. You don't want to go in a circle. You don't want to go back and forth. Just straight, single passes. If it starts to get soaked with dye, you'll fold it to a new clean area, wipe it off, and we want to get most of it. And then get a new towel, spray our cleaner on it, and then use that to kind of do one final pass over the entire part. If you, at that point, if you were to get out your flashlight and shine it at it, if it's a polished surface part, you really shouldn't see any dye reflected. If it's a rough surface part, you should see a little bit of glow, over the entire surface of the part where dye's kind of caught in the rough surface. I think everyone, for the most part, has seen me do the demo with the tan panel that's got the shiny surface and the rough surface. So you kind of saw that contrast between, how clean each of those types of surfaces should get. Method B and D being the post-emulsifiables. Here we, so just an emulsifier or to emulsify is to mix two liquids that basically don't want to naturally mix into a suspension. This is your oil and water situation. Okay, oil and water don't want to mix, but we use an emulsifier to do it. And the one I use, that, again, hopefully most of you have seen, is dish soap, right? You use dish soap to remove fats and oils from your pots and pans and plates and whatnot. And that's an emulsifier. It allows water to clean that away. And it doesn't cause them to actually bind to each other. The emulsifier so dish soap is a lipophilic emulsifier. It binds to the fat. It kind of creates, or the oil, it creates a little sphere ball around the oil molecule, and then allows the water to kind of push it away. hydrophilic bonds to the water and allows it to kind of lightly grab the oil. Okay. So typically good dish soap, any dish soap is going to be a lipophilic. It's really going to grab onto that oil more. Now for dye penetrant, we don't want it to grab the oil too aggressively because it can pull the oil out of the cracks. And so the newer emulsifiers are method D. Those are your hydrophilic ones. They bond and kind of bond more to the water and then allow it to kind of lightly grab the oil molecules, but not so strong that it can pull dye back out. That's got that capillary action pulling it down into a crack. Right? It's basically a weaker bond than the capillary action, the force of the capillary action. Method B are older. They've been mainly replaced by method D, post-emulsifiables. So chemical and mechanical, that chemical action is kind of that surrounding and grabbing the molecule, and then the mechanical action is the water, the oil pushing on it, right? And it was originally designed to reduce the possibility of overwashing rather than having the emulsifier built in. But it can be touchy, but it is really good. We have to use it for those more, those higher level penetrants. Can be washed away too easily that with a solvent or if the emulsifier was mixed in with it. So wash times vary. If you're using method B, several seconds can be the difference between it working or not. So here's B, earliest form, oil-based, greater affinity for oil and water. It actually diffuses into that penetrant, kind of grabs those individual molecules, but it can get pulled down into the flaw with it. And it's very sensitive to application time. What I mean by that is a matter of a few seconds can be the difference between this working properly or being overwashed because it was left on too long. Method D, hydrophilic, it's a later form, came out in the 70s, pretty much what's out there now. But again, that greater affinity for water doesn't diffuse into the penetrant. Rather, it's diffused and mixed primarily in with the water. It's more sensitive. It's more sensitive in terms of better to find smaller cracks and crevices. It's like your level 4 penetrants are going to always be pretty much hydrophilic, like post-emulsifiable. So those penetrants have better detection. And it's also less sensitive to contact and removal time. So it's easier to perform from a operator standpoint. And then you do the final wash with water. So I'm going to go ahead and stop there for today.